This tutorial covers the installation of the MDTF-diagnostics package, as well as running some of the test pods using the package. Before you start, it is recommended that you have already installed either Anaconda 3 or Miniconda, and consult the documentation that is linked below for detailed instructions on installation. You may use a central installation maintained by your institution, but you have to be able to modify the package environments or the ENVs directory to add new content environments required by the MDTF diagnostics framework. You also need to have created your GitHub account and forked the NoGFDL MDTF diagnostics package to your account. Also, bookmark the link to the documentation below and give it a read to get the full details of what using the package entails, as well as how to contribute to it, GitHub tips, and more. The installation description does follow the quick start guide on the GitHub README page below. It is a little more detailed, and there's also a short demonstration following the slides. To begin, you want to create a directory called the MDTF to hold your local copy of the MDTF diagnostics package, the input data directory, and the default working and output directories that hold the temporary files and the pod output. The work and output directory can be the same directory. Next, you want to clone your fork of the MDTF diagnostics repository, or you can use the NoGFDL repo if you are just planning it. The command line steps are below. You can use the GitHub link to your MDTF diagnostics fork, so that would be your username. The SSH link, or you can use the HTTPS link. HTTPS is fine if you just plan on running the framework, but I recommend setting up SSH keys since pushing and pulling to your repository will be considerably easier since you don't have to verify your credentials each time that you push to your repo. Once you have done the previous steps of cloning your repo, you want to navigate to the MDTF diagnostics directory, check out the desired branch or release tag. So again, the steps for the command line are outlined below. Once you have done so, you want to build the conda environments and generate the executable. This is done by running the conda env setup sh script in the source conda directory using the available flags. --all indicates that you will install all of the environment files required for the framework by default. Conda root will be the full path to your conda installation, and then envdir will be to the same path to the conda installation appended with the ENVs directory. The next step comes in handy if you've already built the conda environments and just need to pull in updates for one or two at a time. You can use -e or --env and the base name instead of all to update an individual environment. The base name will correspond to the desired environment file, which has the format env_basename.yml. These files are located in the source conda sun directory. That's the same one that has the environment setup script. This is recommended if you are using the package on a shared file system, as the conda environment installation process can be quite lengthy, just due to the way that Anaconda traverses the package dependencies. We've tried to mitigate this by installing Mamba under the hood. It does help some, but you are still looking at installation times of upwards of 20 minutes on a shared file system if you try to install all of the updates, so just be aware of that. If you're just using a personal machine, installation is a fairly quick process, so on the order of minutes, and this should not be an issue for you. Now that you have the MDTF diagnostics directory all ported to your machine, you'll want to download the sample model and observational data sets for the supported pods and enter it into the MDTF directory. This will populate MDTF input data using the default structure that we're assuming during this installation description. Next, you want to modify the runtime configuration settings in source default test JSON-C to run the desired pods on the data sets. You'll change the case name, convention, first year, last year, and pod list entries to run the desired pods on the target data using your preferred convention for the period that is defined by first year and last year. Next, you'll scroll down in the file and modify the obs data root and model data root paths. The data are not installed in the default locations. Then you'll want to change the work dir and output dir if you want to write temporary files and file output from the pods to a different location. This is crucial that you change it if you have the MDTF-diagnostics package installed, say a home directory, where you have file storage limitations. This may cause errors once you reach that storage limit as you run the diagnostics framework and populate it with output files. Once you have changed the work dir and output dir, you'll want to set the conda root and conda end root paths to the locations of your mini conda 3 or anaconda 3 installation and corresponding environment directory. So these are the same paths that you specified for the conda environment setup script. Now that you've gotten your data and generated your executable and built all the environments, you're ready to run the test cases. So all you have to do is from within the MDTF diagnostics directory, you'll run /MDTF. So this is the executable wrapper that you generated with -F pointing to the default test JSON-C file that you modified. You can also change the name of this file and make your own copy. This will make it easier to track changes that you make to the runtime settings. And then I always recommend appending the -V for verbose option. This will append extra output to the error logs that can be useful for debugging. So this is just a schematic describing the default directory structure we're working with. So within the overarching MDTF directory, you have our MDTF-diagnostics package, the input data directory with the model and observational data required for each pod, and then the working directory, which is also the default output directory. If these are two different locations, they'll have the same structure, but the work dir will mainly just be populated by temporary files that are deleted. And then the output directory will just contain the pod output files. So for input data, in the model subdirectory, you'll have data sets that'll correspond to the case name, so you can have multiple data sets in there. And within each case name, you'll have subdirectories that correspond to an output frequency, so monthly, daily, 6 hourly, whatever they are. And within each of those subdirectories, you'll have your desired files at the frequency required by the pods. In the observational directory, you'll have a subdirectory corresponding to each pod, and then within those pod subdirectories, you'll have the input observational data required to run the pods. In the working directory, the framework will create a subdirectory with the structure case name _ first year last year. And if you run the framework multiple times and do not specify the overwrite option, which is the default of overwrite is false, so you'll create a new directory each time, it will append a version number so you can keep track of the different runs of the framework. In the work dir subdirectory, for each run you do, you'll have another subdirectory for a pod, and within there you'll have output files for the model and observational data, so those will be image files and whatnot, and then in the pod directory you'll have the final HTML file as well as a log file for that given pod. There are several common issues that come with running the framework, so it's good to note first of all that there are 2 error log files written to the work dir So the first will be the case name log file that's directly in the case name subdirectory. That'll contain framework-specific information and error messages. This is the same information you'll see dumped to the terminal when you run the framework. And then there's a second log file that I mentioned earlier that corresponds to each individual pod that will contain pod-specific error messages. If you receive errors about the framework being able to parse a JSON-C file, a pod settings JSON-C, or more likely if you're just running the framework, the error corresponds to the default test JSON-C file you modified. This indicates a formatting error. And you can try identifying the issue by eye, but often it's a misplaced comma or some botched spacing or a bracket issue. It's easier to use an online JSON validator editor. And I've included an example below, but there are several. So pick your validator of choice, copy and paste your JSON file contents, and find your issues and fix your file. If the framework throws an error about an unrecognized command, all you have to do is check that you define the optional command line arguments correctly and or pass them using the correct name. A lot of times it's as simple as you've accidentally included an equal sign between the argument and the option. When you shouldn't. There's pre-processing the metadata in your test data set. Check that the variables contain the required standard name and units attributes. If you are working with a data set that doesn't have complete metadata, you can just bypass the pre-processing step with the disable preprocessor flag as a workaround. The caveat is that the developer, or if you're running on a data set that's not a default data set, the end user has to verify that the input data have the correct units. So this means, at least visually inspecting your files, and then if you're a developer with a pod and working with a test data set, it may help to include a check in your pod to verify a standard name and units are correct. All right, so that said, let's just step through a quick demonstration here of what exactly I was talking about. So I'm using an integrated data environment, or IDE, called Visual Studio Code. There are several IDEs available. PyCharm is another great IDE that's geared toward Python development. So you can see here I've got nice features right off the bat with syntax highlighting. So I'm looking at the default test JSON-C file just for example. You can plug the executable into the IDE that we've generated and provide the command line options and run basically the framework within the IDE and put in breakpoints for debugging. So overall, let's say as an end user, it's maybe not quite as useful, but as a developer, IDEs are invaluable tools to help you along with the process. So that's all I have to say. If you prefer a terminal and text editor, go for it. With that said, you can see here I also have the MDTF-diagnostics drop-down menu displayed here. So here's the actual terminal below. You can see I'm working within my MDTF directory, so I have my fork and my MDTF-diagnostics repo, my input data directory, and a working directory. So just get MDTF-diagnostics. You'll see the contents therein, and the same if I look at the drop-down menu. In the input data, we look at here, that's all linked up. You see I have model and observational data. So here's our default data sets. Let's zoom out a little bit. So here's the data for the CM4. We just have daily output. So I'll expand a little bit more. You can see I have one file for per variable, and there's just, if you go in the default test JSON file, the default pod that runs with this data set is the MJO prop amp data set. So if you want to run this test case, you'd comment out the CESM data set that we've provided right here, and that runs by default, and then uncomment this if you want to test the MJO prop amp pod with the CM4 data set. If you look at the observational data, so here's the supported pods. If you click on, say, convective transition pod, you'll see the input data files required to run this pod. So some .cdf files in this case. If you look at the MGO-prop amp pod, you'll see some .cdf files as well as some PNG files that are used in comparison in the final HTML output. That's what the input data look like. If we look at the default test.json.c file that you modify, so you can see here if we're just running the CESM case, so this is the experiment name, convention is CESM, as an end user. First year and last year are defined here, and then the pod list. So these are the pods that run with this data set by default. So Wheeler Coladas EOF 500 HPA, MGO suite, and MGO teleconnection. All right, and if we scroll down, our OBS data root is given with the relative path. So this is I just showed you the OBS data and model data directories. Workdir is a relative path, so that's where they're the same. So the temporary output files and the final output will be written to that location. And then here is where I would define my paths to my mini Conda 3 installation. And then you can make a variable tarball that'll save the HTML and image plots to a tarball. I usually set this to false because I don't need tarballs for development, but you can set it to true, and it makes it really easy to transfer final output around if you need to do so. And then there's other options as far as saving output that you can change here. So let's see, if we look at the workdir, you can see I have done some testing in the past and run the test cases several times. Regardless, you'll see that within the workdir there's a case name indicated here. So if I ran the CM4 test and ran the MGO-prop amp pod, you'll see here's the log file that corresponds to the framework log. This contains copies of the preprocessed data. This contains model output, so nothing in the netcdf. And then here is where we'd see the pod output. But regardless, that gives you a sense of the overall structure. So that is all for this tutorial.